attending this presentation. So I will provide an overview of machine learning. So here is the outline of what we will be talking today. We provided the collab, so everything in there should be similar to what I am presenting, so they are identical copies. So here's the outline. I'll provide an intro to machine learning, the types of machine learning, and the common tasks that we can solve with machine learning. Then some very common main components of a machine learning system. 3 of them basically: the model, the objective function, and the learning algorithm. And then we will do small activities to build one of these components. Then we will use that to predict diabetes progression. And then we will move on to describing some of the common libraries that are used for doing machine learning. So let's get started. So what is machine learning? So you might, since you are here, you might have a fairly good idea what machine learning is, but just for the sake of completeness, machine learning is the study of algorithms that rely on a collection of examples of some phenomena. So if you have a problem where there is no set of logical rules that you can apply, for example, if you are doing image classification of cats and dogs, there are no logical rules where you could say, okay, if the color is red, then it's or black, it's a cat, and a white, it's a dog. Those kind of rules doesn't apply. You just have to provide the algorithm with a bunch of examples to learn from. So that's machine learning. You might have done in your undergrad courses some sort of searching, planning, reasoning. So those things are not machine learning. Machine learning purely relies on data and examples shown to the algorithm, which helps it to improve. So what are the types of machine learning? So there are a few types. The first one is supervised learning. So in supervised learning, you have pairs of examples. So if you have input images and you want to, and maybe these images of are chest X-rays, and you want to find out whether the image contains a tumor and whether the tumor is benign or malignant. So in supervised learning tasks or type of machine learning, you would have pairs of examples. So you would have an X-ray image and a label whether this is benign or malignant, just like shown here. So we have 3 images, each with a label which says either benign or malignant. Usually the X part in this pair is called the feature vector. So later on, we will be discussing a lot about feature vectors. And so it's good to know that the input part of the pair in an example is the feature vector. And the second thing is the label that we predict, or the target that we predict. So X is the feature vector, Y is a label or a target. So now that was supervised learning problem. How about the case where we have a few examples that are labeled, but a lot more examples that are unlabeled? So in that case, we say we can apply or sort of deal with the problem as a semi-supervised learning problem. So in that case, we have a bunch of examples that are provided with labels. But then there are a whole lot of other examples that just are inputs, that just are feature vectors, that doesn't contain the labels. As you know, labeling is a really tedious task. Like if you have a bunch of images, you would have to bring a bunch of radiologists to basically do the labeling for you. And so semi-supervised learning basically helps us to utilize a lot of unlabeled data as well. But there are cases where there is exactly no labels, like you just only have input data. For example, when we say like there is a whole bunch of text data on the internet, right? And if you want to do any sort of machine learning with just the data on the internet, then it's really hard to sort of do labeling of all the data. So that's where self-supervised learning comes in. So in that case, we just have a bunch of feature vectors, and we extract the labels from the data itself. So you might have heard ChatGPT or large language models. So what they do basically is having the previous words, it predicts the next word. So the next word in a sentence is basically the label for the data. So the self-supervised learning algorithm basically exploits the property that you could extract labels from the data itself. And usually the goal of self-supervised learning is to sort of learn a good representation of the feature vectors or the input data. And then you can use that to do some sort of supervised learning tasks. So one example of this self-supervised learning I mentioned, that you can have like the previous words and the next word becomes the label for the data. But can you think of any other example where you could extract labels from the data? So here is a really cool example where if you provide two inputs to a model, x1 and x1, and if they are the same examples, then it's the label is true, and if they are different examples like x1 and x3, then it's false. So it's sort of a way to do representation learning. We will see more concretely the supervised learning algorithms, and then you will understand more. But this is just to give you a breadth of what's possible. And then the fourth type of machine learning problems is unsupervised learning, where again you just have unlabeled data, but in this case you don't try to extract labels from the data. You just want to find patterns in the data. And what is this good for? It's good for finding whether a new feature vector, a new input that comes in, is it an outlier? Is it belonging to a certain cluster? Things like that. So you can use unsupervised learning to basically answer questions like these. Now, these are not the only sort of learning problems, but this is an introductory lecture. And so I'll just list a few other important classes of machine learning. Here, reinforcement learning, active learning, transfer learning, continual learning. And there is so much research going on that you can put any word in here and follow it with learning, and you will find some research papers or some applications of this type of machine learning. But it's good to know at least that these are all falling under the category of algorithms that learn from data. Okay, so those were the types of machine learning. So what common tasks we can solve with machine learning? So with supervised learning, there are a bunch of tasks: classification, regression, recognition or detection, segmentation, and time series modeling. We will look into these a little more in detail in the next slides. And then in the unsupervised learning case, there is clustering, dimensionality reduction, and outlier detection. So let's look into classification. So we have already seen some examples of this, but let's say you have some input feature vector, say it's an image, and you have a target that comprises of a finite set of elements. So for example, in the example we saw previously, the input was an image and the target was either a benign or malignant target. So that's the basic classification problem. Now, if we have a problem like this, where there are only two targets, it's called binary classification. You could have multivariate classification, where you have more than two outputs, and you can have multi-label classification, where a single image could have two outputs. So, for example, if you have Stack Overflow questions and you want to tag it, so a single question could be tagged with multiple sort of outputs. So that's multi-label classification. Now, moving on to regression. So in the case of regression, the input is still sort of a feature vector, let's say an image, but the target is continuous value. So you could have an infinite number of output values. So for example, like if you are doing crowd counting sort of application, so you take an image on an airport or some common lounge, and then the target is a count of the number of people that you want to predict. So the number of people could be 0 to 100 or 1,000. So there are sort of almost an infinite number of outputs. Another example would be the housing price. So if you have the input is the area in square feet, and then the target is the dollar amount the house will cost. So it's again a continuous target to predict. So that's a regression problem. Recognition or detection is another problem, which is a more sort of compound problem where you basically combine regression and classification. So here is an object detection example. So here you see that the laptop has a bounding box, and it has the label laptop. So that's a classification. And then the positions of these bounding box, like the start and the width and the height, or the anchor and the width and the height, are basically regression targets. Segmentation is another sort of really cool application. So if you have an input image, you want to segment different components of that image. So you could decompose it as a classification problem where each pixel either belongs to one of the many objects or clusters. And then the last one is time series forecasting. So if you have data of certain phenomena up to a certain point, and then you want to predict the same quantity ahead in the future, so forecasting date for the future. So that's a time series forecasting problem, and they could be framed as a regression problem, but it's more complex than simple regression. And then moving on to the unsupervised cases. So clustering is another problem or common task that is solved with machine learning. And so let's say you have two features in your feature vectors, so feature 1 and feature 2, and you gather a bunch of data, and in 2-dimension it is easy to visualize, but let's say you have a whole bunch of features, and now you want to sort of cluster similar things together, or find what features or what feature vectors are belonging together and which ones are separate, so that you could do, if let's say this is a marketing campaign, you could sort of target your advertisement to a specific group, or if it is some medical problem, you want to sort of apply the same sort of experiments on the same set of patients, so things like that. So clustering is used to basically cluster examples into similar groups and separate them from groups that are different. So now the exciting part. So we have seen the types of machine learning, the supervised versus unsupervised, and the common tasks like regression, classification, clustering, and so on. Now those are very much at a high level. You need to sort of know whenever you are working with machine learning, you need to know, given a business problem or any problem, you want to evaluate whether there is data and what kind of data it is, and what kind of or what type of machine learning you are going to apply. And sometimes it's a combination of multiple types of machine learning, and then you identify, okay, what task do I need to solve with machine learning so that the business problem or some other sort of academic problem that I'm solving will be resolved. So you have done that problem formulation up till now. Now we need to look into, okay, how do we actually do this work? So here we look at the components of an ML algorithm. So there are 3 components in an ML algorithm. So there are deviations, but this is the most common case. So the first one is the model, the second objective function, and the third is the learning algorithm. So the first thing you do, given a task, is to create the class of the models. And we will look into the classes of models. So you might have heard the name neural networks or decision trees. So that's the class of the model. So when you decide whether it's a neural network you are going to use, you basically decide the class of the model. And then you have a learning algorithm. So basically what the learning algorithm does is it picks one of the model in this class of models. So out of all neural networks, the learning algorithm will pick one single model for you. And how does it do that? So you would define an objective function. And an objective function is a function of the data set that you have and the model that you pick. And then the objective function basically tells you how good is a given model based on this data. And the learning algorithm basically searches for the best model using this objective function, and then provides you with the best model that it can provide you. So we will look into more details on each of these three components in the coming slides. So the first one is the models part. So what does a model basically do? It basically relates inputs to the output. So giving a very simple example, the linear regression model. So you have x's as the inputs and y is the output. So x is a feature vector with components of x1, x2, and x up to xn. And so you are predicting a quantity y. And you could multiply these input features with some weights, W0 to WN, and you compute the output y, and it's your linear regression model. And graphically, if your weights were just 0.25 and your feature vector was this one, so it just shows how do you compute this linear regression model. We will look into how to compute these weights, but that's part of the learning part. So let's just look into the linear regression model given the weights. So here is a sort of a simple activity. If you are given sort of the task to implement linear regression model, so in your notebooks, you might already have this implemented, but I will sort of try to code here so that I can explain these little sort of things and you can understand better as to what is happening. So here is a function, linear regression model. All of this is in Python, so hopefully everyone is familiar with Python, but it's pretty simple enough to sort of understand if you are familiar with any programming language. So here is a function, linear regression model. It receives an input x and some weights, and we need to compute the output. So output is basically the y variable that we defined previously. So we will loop over the input dimensions. And so here is the I from 0 to length of the input. And then we will just compute the output equal to output plus the input I times the weights I. And so this would be pretty much similar to what we have there. So we have the output equal to the input times the weight times the input. So if I were to really go exactly the same, then I would just to correspond to the formula. So of course there are more clever ways to do this, and sort of like this. I'm boiling down everything to like really the simplest way, so that it's easier for everyone to understand. Of course, you would do this more efficiently and in a vectorized form if you are familiar with more Python and NumPy and other libraries. Okay, so that's our linear regression model. So that was good for regression problems, but what if your problem is a classification task? So, for example, detecting whether there will be rain tomorrow or not, or whether a tumor is benign or malignant, or other sort of classification problems. Then what do you do then? So for that, you use logistic regression as one. So for those, there are like classes of models, and logistic regression is one class of models. And it's really similar to linear regression, except that you pass the output of the linear regression through this sigmoid function, and this gives you a probability of the class uh, of the value of the output variable being 1. And what is this sigmoid function? It's basically 1 divided by 1 plus e raised to the power minus x. And it basically gives you a probability distribution. So here you see the sigmoid function. At minus infinity, it's 0. At plus infinity, it's 1. And in between, it's monotonically increasing. So that was logistic regression, but how about like other models? So decision trees are very popular, and you will hear about them very often when you work with any sort of practical machine learning problems. So what is a decision tree? So it's basically a set of decisions, if-else statements, if you will. And so if we have, let's say, features A and B, like these are the inputs, we can define some thresholds, like, okay, is A less than the threshold T1? And if it is if it is no, then the output is 0. And if it is yes, then is B less than threshold 2? And if the answer is yes, then the output is 0. Otherwise, the output is 1. So any computer scientist or someone familiar with programming would be able to know, like, okay, these are just if-else statements, which is fine. So where is machine learning in here? So the machine learning part comes in for deciding what would be the value of T1 and T2, and whether you should ask a question about A first, or you should ask a question about B first. So which feature is important? And so how many sort of times you should ask these things. So those are the questions that machine learning answers for you from data. Sometimes people joke about like AI is just if-else statements, but yeah, it is. Everything is almost if-else statements, but there are components that are learned from data. Another sort of popular machine learning, classical machine learning algorithm is support vector machine. And it's basically similar to the linear regression equations, but it is a classification model. So it provides you a one label or a +1 label and -1 label based on whether the output of the regression equation is greater than 1 or less than 1. There is more theoretical details of how does it sort of work, but just to give you a simple overview, if you have that regression vector or equation, then that defines a line. And basically, the support vector machine draws this line between the two classes. So if you have the blue or the +1 class and the -1 class, then the support vector machine tries to draw a line which is away from both classes equally. And it's sometimes called maximum margin classifier. But the important thing is to just know that it is a class of models that you could use or pick from. And the final class that I'm going to discuss is neural network. And neural network is basically, again, your regression equation passed through the sigmoid function. So this would be very similar to the logistic regression that we described, but then doing it multiple times. So this would be the logistic regression one time and multiplying with this hidden layer weights, is logistic regression a second time. And that basically is your sort of neural network. So if we look into this one node, these are the inputs. This one is doing logistic regression. This one is doing logistic regression. This one is doing logistic, and so on. And then here, all the inputs are coming, like all the logistic regression outputs are coming from these middle layers to the output. So if you know how to implement linear regression, if you know, then it's relatively simple to implement logistic regression, and then it's relatively simple to implement neural network as well. But so we have seen, just going back to the slide with an overview. So we have been looking at this part, okay? Like we looked at linear regression class, logistic regression class, decision trees, SVMs, neural networks. So you might be thinking like, okay, which one do we choose, or what are the differences between these different classes? So that's the model capacity. So an important property of classes of models is what kind of input target mapping can each model represent, or each model class represent, and what kind of decision boundaries can each model class represent. So here are some examples of what is possible with each of the classes. Somehow it's okay. So here, logistic regression, as we see, the blue and the yellow areas are basically two classes. So, and based on the model, so the model will classify any input that lies in the blue region as the blue class, and yellow, in any example that falls in the yellow region as yellow class. So as you can see, the logistic regression can only do linear boundaries, so it can do straight lines. But decision trees can do arbitrary sort of, you can have if-else statement on very arbitrary sort of regions. And so decision trees can really sort of make these arbitrary sort of rules for you, or decision boundaries for you. And so in terms of capacity, logistic regression, it has less capacity versus decision trees. Random forests, which are a bunch of decision trees, are somewhat more smoother, or like less sort of regionalized than decision trees, but still they are still very much like able to do arbitrary boundaries. Support vector machines provide you really nice and sort of nice boundaries, but this is a variant of support vector machine. And then neural networks also provide you continuous boundaries. So this is some of the sort of the intuition as to why when you will use which model. So if you have simple linear relationships, then for a classification problem you could just use the logistic regression. But if you encounter that, oh, you have very sort of nonlinear relationships, then probably neural networks or some other models might be the best to use. Okay. So this was all about the model classes. Now, next we look into the objective functions, because we decide on a model class, let's say linear regression. Now, how do we get those weights for our model? Because we decide on the class, but which weights should we use? So that's the to basically find that out. We need to use to find that out. We need to use an objective function. And basically, the objective function is used by the learning algorithm to evaluate different models in a given model class. And it's a function of the data set, the data that you have, and the model. So here are some mathematical notation, but it's basically we have seen most of it already. So given a model class H, which is basically let's say all linear regression models, we need to choose one, or like look at the linear regression models one by one, right? We have a class of models, which is linear regression models, and one particular setting of the weights would would basically be denoted by H. And then we have a data set, which is a pair of, which is a set of pairs of examples with inputs and outputs, targets pairs. And then we need to sort of figure out a way as to how good is the model on I example. So that's our cost for one example. So if we have the target label and we have the model and we input the feature into the model and it predicts the output. So we have the actual or the real output or the target, and then we have the model output. And so somehow we need to define a function J, which basically tells us how well did we do. Like the actual answer should be yi, what did the model output? And this is for one example. How about the whole data set? So if there are n examples in the data set, we just sum over all the costs for each individual example. And that's our objective function. Now, there could be different types of objective functions based on what value do we sort of assign to this, or what function do we use. So there are some common objective functions, such as the mean squared error for regression tasks and cross entropy for classification tasks. So we will look into the mean squared error for regression tasks in more detail in the coming slides. So what is mean squared error? So given an example, let's say xi, yi, the model predicts yi height. And a good model will produce yi height, or the approximation close to the actual target yi. And so we need to sort of represent the error, which is yi minus yi height. And this could be, the approximation could be either larger or smaller. And so how do we encounter for like larger or smaller? So we can take the square of this, and then anytime it's either larger or smaller, we would have a positive error. And then we need to sum it over all the data set, basically take the mean of it. So we basically take this is for one example, and then sum it over the I or the n examples for I from 1 to n. And here it is assumed that this approximation is by this model H. So given a model H and a data set xi, yi, like a set of pairs of examples like these, we should be able to implement the mean squared error. So that's basically our next activity as to how to compute the mean squared error. So we are, here is the function, compute mean squared error. We have the actual targets and we have the predictions from the model. So how do we compute the mean squared error? So first we need to compute the error. So the error, and since there would be a whole bunch of these targets and a whole bunch of these predictions, so these are two arrays. So we need to find what the length of these arrays is. So let's say n is representing the length of the array. And then for each of this array element, what we need to do is to find the error, right? And the error would be y target of I minus y predicted So that's the error, but we said we would be looking into the squared error. So the squared error would be error squared, and then we need to compute the mean squared error. So for computing the mean, we will first compute the sum. So sum squared error. And if this is equal to 0 in the beginning, and then we continually sort of add the error for and now how do we compute the mean squared error? So we can just, if we have some squared errors, we can basically just divide the sum squared error by the number of examples, and that's our mean squared error. So it's a sort of a very lengthy way of doing this, but hopefully it gives you a better sense of what is happening here. Just to be more explicit, just do this. Are there any questions that needs to be addressed, or are we good?
There's multiple questions in the chat. Do you want to go now or later? Probably now is a good time. Yeah.
Okay.
Thanks, Sebastian.
Yeah. So first question is, are objective function similar to loss or cost functions?
Yes, exactly. So they are the same thing. The objective function, the cost function, and the loss function, they are the same thing for most purposes. Yeah.
Okay. And then there was a question about the decision tree. Why in the decision tree was no equal to 1 in the first case and number equal to 0 in the second case? Is that significant, or is it just an arbitrary example? Yeah, I think it was an arbitrary.
It was an arbitrary example. Yeah, it's just one arbitrary example where, like, if you have some problem, let's say, how to say, like, let me, since I have coffee in front of me, so I'll give you a coffee example. If the color is the color darkness is like less than some value, then it could be like dark coffee or like dark roast. But if it is not, then it's like y equal to 0, so it's not black coffee. And then even if it is like the color is less than some sort of darkness, then is it sort of in a mug or like some other feature, like is it shiny? And if it is shiny, the color is shiny, then it is like a dark coffee. Otherwise, it is not dark coffee. So something like that, like any arbitrary sort of problem could fit into a decision tree. But then the question is, what kind of questions do we ask? So we know we can do the color of the coffee and the temperature of it and the sweetness of it, but which question should we ask first, and what should be the threshold? Like, okay, when you say dark, how dark? So given a set of examples, like having a whole bunch of data set of coffees and their features and their labels, then we can construct this automatically.
Thank you very much, Dr. Khan, for this beautiful example with coffee. We have another question for neural networks. Is the input layer doing logistic regression as well, or is it just a hidden layer?
So that was just an example as to, like, in sort of in programming, how would you implement? So this if you basically strip it down to the basic neural network single neuron, so each of these basically are doing a logistic regression on its inputs. But overall, it's like logistic regression is a linear model, but overall, when you have the output of this one as a function of the input, it's non-linear. So it's like output as a function of the inputs is not doing logistic regression, but output as a function of the previous layer inputs is doing basically logistic regression if you use the sigmoid sigmoid nonlinearity. So there are sort of caveats to it, but in the simple sense, yeah, that's basically.
Thank you. And I think Dr. Maliki answered some question. We have another one, which is, how could you improve a model using an objective function? How would a model develop? Would it be effectively adding more test cases to split input data better?
Yeah, so that's the next slide. So if there are other questions, then we can sort of move to that. Otherwise, the learning algorithm basically selects the model, and so the objective function is used to. So that's my next topic. But
yeah,
there are
okay. So I think you can keep going. We're good for now with questions.
Okay. So so we have implemented a simple or a very popular objective function, the mean squared error. And so now we are ready to go. So we looked at a bunch of models, classes, so linear regression, logistic regression, neural networks, and so on. And we implemented one of them, the linear regression. And we looked at the motivation behind objective function, and we implemented one of them, the mean squared error. Now is the time to look at, okay, how do we pick a single model out of all the linear regression models and then use it as our model. So that's the problem of the learning algorithm. So what does the learning algorithm does? It basically, ideally, selects the model that minimizes the objective function. So so if we have the weights or the parameters of the model, W, then and the objective function J, then and a data set D, then basically the learning algorithm basically gives us the optimal weights W that will sort of provide us the minimum objective function or loss function or cost function. So if we have, let's say, n samples, x1, y1 to xn, yn, we find a model with the lowest objective function x star. And when we observe a new input x, we can guarantee, can we guarantee anything about hx? So we trained, or the learning algorithm trained or picked the model based on this n samples. Can we guarantee anything about any new thing? So let's say we trained a model on purchase of, or let's say we trained a model on predicting how much sales would be there for outdoor activities or maybe even indoor activities, and then COVID happens, and then we have a new example. Can we guarantee anything about whether the model will do the predictions correctly or not? So that's like, if you can't guarantee that, then machine learning is of no use, right? But can we mathematically, in general, we cannot make such inferences from the observed to the unobserved. So that's a basic sort of thing that we need to understand, that we cannot make general sort of claims like this, but we can do some assumptions. We can make some assumptions that helps us to sort of do inferences to the unobserved cases. And what are those assumptions? So that's the independent and identically distributed samples. So what it is, first is any sample from the data is distributed according to a probability distribution D. So if you have any input and target labels, it is assumed that it will be coming from a given fixed probability distribution. And then the second assumption that we make is that the samples in the data set are independent of each other. So if you have a housing price sort of, if you have a house and it has some price, then that example is independent of another house with its own price in the data set. So basically the examples in the data set are independent. So these are, in some cases, these assumptions make sense, and in other cases, it doesn't make sense. And so it's for the machine learning practitioner to basically keep this in mind, that if you are applying an algorithm, you should ask these two questions yourself. Okay, so given, let's say, coming back to the problem of the learning algorithm, where we have the cost function, the data, and the parameters of the model, and we want to find the best parameters. So how do we do that? So we use some sort of optimization algorithm, and gradient descent is a common optimization algorithm, which could be used to train or basically do learning for a whole bunch of classes of models, including linear regression, logistic regression, SVM, neural network, and whatnot. So let's look into what gradient descent is. So imagine this is the landscape of the loss function, and let's say you are right there at the top. Let me pick my. So let's say you are standing here, and this is the cost function, and your goal is to get to some goal state, like let's say this is the minimum of the cost function. So this is your target here. And so what would you sort of, if you were there, what would you do? You would find, if you were not afraid to fall, of course, you'd find the steepest direction in which, or the steepest direction in which you could go down, right? So it would be something like this. You will take steps in this direction because this seems like coming down the quickest. And when you reach here, you'll take steps, and when you reach here, you wouldn't want to keep going in that direction, right? Like you would want to stop there. You wouldn't go this way, like here. No. What you would do is you would change the direction, because now the steepest descent direction is this way. So you would come here, and then you will sort of reach your sort of lowest point in the loss or the objective function landscape. So this is basically what the gradient descent do. And so we will look into this idea more mathematically in the next slide. Oops, how do I clean this up? Okay. So here, this idea is presented more mathematically. So we initialize, we start with some random place. So on that hill, we would be somewhere randomly placed. And then we start with sort of taking steps until we reach the target. And what steps do we take? We find the steepest direction, which is ascending, and then we go in the negative of that. So the gradient basically gives you the steepest ascent direction, and then you take a step with like mu. Mu is the sort of the step size or the learning rate. With that step, we take the descent. We take the step in the descent direction. And so that way we find our new position, WT plus 1. So that's basically the sort of the intuitive way to look at the gradient descent. Of course, you want to, one of the things that you might sort of, when you do practical problems or doing like actual model training, this step size, or how quickly you sort of jump from one point to the next point, is very.
Hi there.
I'm gonna mute this page.
Yeah. So that's really important to sort of set the learning rate to a reasonable value. And why is that? So here is an example. So if you have a small learning rate or a reasonable learning rate, you would take steps, and you will eventually reach the minimum point and then converge there. But if you are taking like two quick or large steps, then you would just jump around the minimum point, and you would never converge on it. But if you take it like, if you take really small steps, so if you take the extreme on this side, then you would just like be there, like just moving slowly there and never reach the target. So this learning rate parameters is really important in all these learning algorithms. Okay, so now we mentioned that that the cost function is a function of the, or the objective function is a function of the data set and the model that we have, and then we need to compute the gradient in order to learn the best model. So how, if we have the mean squared error is the objective function, and in the previous slide we saw that we need this component, which is the gradient. So we need to somehow compute, given j, compute the gradient with respect to w. And so how do we do that? So if we take the derivative of this equation with respect to w, so it's like the 2 goes in front, so it comes here, and then you have yi minus wxi, so that's there. Remember high school sort of differential equations or calculus. And then you have minus wxi, which becomes, with respect to, if you differentiate with respect to w, it becomes minus xi. So finally, you have this, you can move this minus inside here. So you have wxi minus yi. And remember, wxi or w times x is the model output in our case, the linear regression. So this is basically the equation for your gradient computation. So let's implement this equation now. So I have the inputs as the x is a matrix of x is a matrix of input feature vectors, and y is the targets, and weights are the weights of the linear regression model. So first, I would want to compute, like, or find out like how many examples do I have. So if I do length of x, that's the number of examples that I have, and y would have the same length. Y would be the same. So that's m, and then we want to predict a label for each of these examples in x. So how do I do that? Let's say I have model predictions as a list, and then I go for each of the example for I in range of n. For each of these examples, I do a prediction using my linear regression model that I defined above. This will give me a prediction. So I need the input to this model, and I need the weights, because the linear regression model takes the input and the weights and computes the output or the prediction, and I can just append to this list. And this way, I would have m predictions. And now I have this. I have to calculate the gradient. So the gradient is, in the beginning, it's set to 0. And then looking at the equation, if we look at the equation, so we have xi now for all i's, and then now we need to subtract the actual y and then multiply it by the xi and do it from 1 to m. So I'll do for I in range m, if gradient is equal to have the model predictions I minus the actual target or the target label, and then I need to multiply it with x of I. Okay, and this gives me the sum of gradients, and then there is in the formula on the previous slide, we have a 2 divided by m as well. So to complete it, I'll just do gradient equal to, okay. So hopefully I haven't made any mistakes. Yeah, seems like it. Okay, so hopefully everyone sort of following along to some extent as to what is happening here. We basically just implemented this formula where h of x is the linear regression model with weights W. Okay, so now we have the formula for the gradient. We have this gradient formula, but what we need to sort of look at this gradient descent iteration. The new weights are equal to the previous weights minus mu times the gradient. And so now our next task is to implement the stochastic gradient descent algorithm. And that's here. So it's easy because we have all the components now. So we have the gradient, which we just can compute it. So compute gradient, this is the function that we just coded in the previous slide. So we provided with the training examples and the training targets and the weights of the model. So that's sort of gradient. And then the new weights would be equal to the previous weights minus learning rate times the gradient. And that becomes our new weights. And so this is the one step of the gradient descent algorithm. Okay, so any questions so far before we apply what we have learned so far into
We have some questions in the chat. Some have been answered by Dr. Maliki, but maybe you can answer some out loud as well. So one from Umar: does the learning algorithm optimize each model to determine the best model, or does it determine the best model and then optimize that model?
Yes, so I will draw here. So it's if you have a basket of models, let's say X, Y, Z, W, P. So this is this is the neural network basket, and here is another sort of basket of models. Let's say linear regression, and these are like 1, 2, 3, 9. So these are different models in there. So what the learning algorithm does is, given your data, given the data set that we have, it picks one of the models. So given the data, which model, like if we have decided that we are looking at this linear regression class of models, then which one is the best one given my data and the cost function. So it basically picks one model, and the way it picks it is using the optimization algorithm. So the optimization algorithm basically looks at all these models or a subset of these models and says, oh, model number 2 has the best cost function, and so you should use model number 2. So that's the relationship between the optimization and the learning algorithm. Hopefully that answers the question.
I think you did. We have two other questions. One from Anna. it seems that all the weights change by the same proportion because one gradient is used. How does that work in complex situations?
Yes, so that's a really good observation, and it's like a sort of an active area of research. First, the gradient would be it's a gradient vector. So based on how many weights are there are like different dimensions to it. So the gradient becomes a vector. But the other thing that's really important is the learning rate. So the learning rate is this constant, simple one constant that we are using here. But an active area of research, at least a few years ago, was to have different learning rate for different dimensions and at different steps. And it's called adaptive learning rate. And this here, we are just introducing the concept. So we are doing just simple stochastic gradient descent, but there are algorithms such as ADAM optimizer or RMS prop. So there are other algorithms that does basically go into much more detail as to how to sort of tune this learning rate. So it's like taking a step, but every time you take a step, you calculate, okay, how big a step should I take? Whereas in here, we are just setting it to a constant value. Hopefully that gives some perspective.
Thank you, Dr. Khan. And then last question on the chat for now is from Farzan. It actually is about the optimizer, ADAM optimizer, sorry. So using optimizer like ADAM would not ending up too struggling at local minimum and prevent our model to find the global minimum? If it is possible, how can we fix that?
Yeah, so that's probably for an introductory sort of lecture. It might sort of we are discussing the local minimum and the global minimum in the future slides because we are looking at the training and the test set. But that's true. Like if you use any of these stochastic gradient methods, it doesn't matter whether it's ADAM optimizer or some other optimizer. You run the chance of like getting stuck in a local minimum. And just to give some context for everyone who might not be familiar with what we are talking about. So if you have a function like this, let's say like this. So if you start here, let's say if you start here, your algorithm will sort of bring you here, and this would be our local minima because here there is no sort of on both sides, you are like your cost function is increasing, and if you have a low enough learning rate, then you will just get stuck in here because there's no way to get out of it. So this is our local minima, but we know from this picture that the global minima is this one. So for any of these machine learning sort of stochastic gradient methods, these are, especially if the models are non-linear, not for logistic regression, because the logistic regression or the linear regression just have this kind of loss function. But if you have neural networks, you could have these sort of local and global minimas, and so that's a problem. It's a sort of a research problem that you can never sort of be certain in non-linear models to have a global minima. But it doesn't sort of affect our conversation here.
Thank you very much. I think you can keep going now.
Okay, so we have done a bunch of things. We have a model class, we coded a model, we had a learning algorithm, and we have an objective function, the mean squared error. So what is this all for? Let's put them into use. So we will use what we coded so far to do some predictions, and we will predict diabetes progression. So let's say we are given a data set of 442 diabetes patients, and the data set consists of XY pairs. X is the feature vector consisting of features like age, gender, BMI, average blood pressure, and other blood measurements. And Y is disease progression 1 year after measurement. So is it 20% increased or 20% decreased after we measured the patient's the patient. So when the previous, in one of the slides above, which I have skipped here, I do some data pre-processing so that we have this data readily available. So if I run this command, it will give me the training examples and the validation examples. So let's look into some of the training examples. So if I have train x of 0, y of 0. So I see that x is an array of things, and y is a label 151, which means 1 year ago this patient was taken to the the hospital. They did some tests. These are the results of the measurements, and 1 year after, their diabetes level increased by 50% or something like that. And so now we need to, given a new patient, if we take them to the hospital, can we predict what would be their condition 1 year after? And so that's the problem that we are solving here. So we have coded. So as we see, it's a regression problem, and we can just apply the linear regression model that we have developed so far. So the class of model here, I'm just making this decision that the basket from which I'm going to pick the models is linear regression. And so that's our the class of models. And then I need to now, using this data, train a specific model, or like pick the specific model that I will use for predictions. So what defines the logistic regression model? It's the weights of the model, right? And how many weights should be there? It's basically the length of the feature vector. So if I have the dimension of the feature vector, let's say first feature vector is 0, 1, and if I take the length of that, that's my dimension. So basically what I'm saying, how many elements are there in this feature vector? So that's d vectors. And now I need to have d weights as well. So that's the weight vector for linear regression. And then I need to find, given the data set, I need to find the new weights. So weights equal to form gradient descent. This algorithm we just implemented in the previous slide. So we provide it with the training data, and we provide it with the weights. So currently we started at 0, 0, or like all weights equal to 0, and then we perform gradient descent with this weights and some learning rate, which is set to a default value of 0.1, and then this gives us the new weights. And so given this, given these weights, we can do something like this, like logistic regression model. Remember, the logistic regression model takes in the input. I'm just providing it with, let's say, the input 0 and the weights. And this should hopefully. So I have new weights. So I have, so what I'm doing here is I have weights initialized to 0, and then I have new weights that basically calls the perform gradient descent algorithm once and computes the new weights. And given these weights, what's the actual name of the model? Linear regression. So given these weights, I know that I have the output that the output would be 30%, but let's look at the actual value of the target. So if I say train y of 0, so its value should be 151, but it predicted only 30. So that's because we just did one step of the weights, right? So I want to do like a whole bunch of training. So let's say I want to train for, let's say, 1,000 steps. And what's the issue here? Okay, so it's training for 1,000 reps, maybe too excessive. And let's see if our model have trained a little better, whether the weights are a little better or not. So we see that it's closer than before. So it's not exactly the same, but better. We started with weights of 0. So generally it's good to not start with 0 weights because they just messes up with the optimization. So let's start with something, some weights that are random. So let's say for let's initialize the weights with some value, random values. Okay, so if for each of the weights that we previously initialized to 0, we set it to some random value, and let me reduce these to 500 so it's quicker. So it's with random weights as initialized, it has improved a little bit to 151 versus 166. So now if you are taking if this model was sort of course this is a toy model, but you see the point, right? Like if you take the measurements today, you would ideally, like you would want to know that next year this time your diabetes progression would be 50% more than currently, but it's 60. The model is predicting 66%. So it's not the perfect model, but it's just a toy example that we just implemented over the last 45 minutes. So it's, or 1 hour. So that's pretty good. Okay, so that's the part that I wanted to sort of go over. In terms of more theoretical, we are moving towards the machine learning libraries so that you don't have to code all of this every time and use some pre-made libraries that you can just use off the shelf. But before going on to date, if there are any questions, I'm happy to answer.
Feel free to ask your questions on the chat if you have some. I think for now there is no question. Maybe we'll have some at the end of the workshop. Or
okay, cool. So we have looked at an example, and we have coded one, but every time you come across a machine learning problem, you don't have to go through all this sort of mathematics and sort of doing the gradient descent to yourself and all those sort of things. The people have done it, and you just need to use it. So one of the really good library is in Python is scikit-learn. And it implements almost all algorithms, or many of the classical algorithms that you might come across. So here is sort of an overview slide of the library on the library website. And so if you come across any sort of regression problem, you could just use these regressors from the library. So the SGD regressor that we just implemented is already implemented there. There are support vector regressors, other sort of elastic net, and so on. So the name there are an infinite number of or a large number of algorithms out there, and you just need to sort of learn how to use this library to basically use those algorithms. So for regression, you have SGG regressor. For classification, you have support vector machines or support vector classifiers, SGG classifier, naive Bayes. These are basically different classes of models. For clustering, you have k-means clustering. Similarly, for dimensionality reduction, you have a bunch of algorithms such as PCA. So let's look into how to use this this library then. So we will be using the digits or the handwritten digits data set. So here I'm going to just visualize the data set a little bit. So sklearn, we import the data sets and then load the digits data set from there, and it returns us a pair of vectors. One is the input matrix and y is the labels. And let's look into the lengths of these. So we have 1797 examples. And let's plot some of these. So if I plot the the 13th example in the input and plot it using an image, so I see this this image, which probably, if you are using a machine learning algorithm, it should probably detect that it's a 3. Let's look at another example. Let's say look at the 17th example. Well, it's hard to know which one it is, but probably it's a 4, and so on. So, yeah, I think it's a 6 or an 8. I don't know. Let the machine learning figure it out. But we can, of course, look at the label of this this example. So what is the 18th label? So it's an 8. So in the data set, it says it's okay, cool. So that's just some visualization of the data set that we are going to work with. And so what problem we are solving here is given given an example of like an image of handwritten digit. So what we are trying to do is like having an input is an image of the handwritten digit. We need to classify into 10 classes, whether it's 0, 1, 2, or 9. So that's the problem that we are solving. So as you see, it's a classification problem, and so one of the models that we use for or like discussed in the classification tasks is logistic regression. And it's super easy to use a logistic regression in scikit-learn. You don't have to go through all the process that we went through for the problem of linear regression that we went through. So here is sklearn .linear model, import the logistic regression, specify how many iterations that you want to train it for. So here it's set to 100,000. And then given this logistic regression classifier, we just call the fit method on the classifier and provide the x and the y, the inputs and the targets. And this basically trains the model for us. And then here I'm going to print or display the image as input, and then use that image to do a prediction. So let's do this. So here it's going to train the model. It will take a few seconds, hopefully. And then here, so the 100th input example is basically this image, and the model classified it as a 4. So let's do the 105th example as the input. Well, I shouldn't be training it again and again. I could just do the, anyway, yeah, that's fine. So the model predicted a 9 for this, but what was the, let's see, what was the label for this? Because I can't understand whether it's a 9 or something else. Yeah, it's a 9. So the model predicted a 9, and the actual label of it is also a 9. Okay, so now we have like just in 2 lines we can do logistic regression, but how do we evaluate like whether it was good, like whether the model, the classifier is good or not? And so how do we evaluate? So there are a bunch of metrics for evaluation, and the first simple one is accuracy. So it's basically correctly classified examples divided by the number of all examples that we present to the model. And so scikit-learn has like these accuracy metrics. So you could scikit-learn dot metrics, import accuracy score, and then you have your model predictions, and you can easily just provide the actual labels, the Y, and the model predictions, and it will give you the accuracy. And it says 1.0. That seems suspicious, because that means the model is 100% correct. So why would they be? In machine learning, you never have like 100% accuracy, because you never have certainty that, okay, my model will always work. It's always like less than that. So maybe something happened there. So the question is, did our model cheat? It's like giving the exam to the sort of the model, which it has already seen. So that's the problem there. So what we need to do in any machine learning sort of problem is we need to have training and validation data sets. So we have the original labeled data set. We split it into a training set, a validation set, and a test set. We use the training set for training the model. So like the fit function will receive this training set. And then we define whether we would use a neural network or a logistic regression or a decision tree based on this validation set. And once we have made our final decision and we are going to ship the model to like a production, like for business, or if we are publishing a paper, we need to report some numbers. So that will be this test set, which will be used for that purpose, so that there is no impurity at all in this test set. So how do we split our X and Y, like the data set that we have? We can use the test split method from scikit-learn. It provides you with an option to sort of specify how big the test size will be. So I'd say 15% is the test size. And then given that split, we can measure how many training examples we have here and how many validation examples do we have here. So we have 270 test set and 1500 training set. So now we can print here, doing the same thing, but printing the accuracy score on the validation set and not on the validation set and not on the training set. And now we see that our model is accurate 95% or 96% of the time. How are we doing on time?
We are very good on time.
Okay, cool.
You have a couple of minutes, and also students have already asked questions. So if you have less time for Q&A, that's completely fine.
Okay, cool. So this worked well for sort of accuracy is good when you have equal number of data for per class. So if you have like 10 digits and every digit is represented equal amount of time, then the accuracy reflects a good metric. But when you have unbalanced classes, so for example, if you are doing cancer sort of detection, then if you have a bunch of x-rays, a lot of them would be just benign tumors and only a few of them would be like malignant. And so if your model always says like, oh, it's benign, then your accuracy would be fairly high. Let's say 99% of the data is like benign and 1% is malignant. Then in that case, if your model always says the output is benign, then your model's accuracy would be 99%, which is misleading because it's of that model is of no use. So To deal with this case, we have certain other metrics such as precision, which basically discounts the false positives. So if it is not malignant, but your model is saying it's malignant, so high precision would reduce that. A recall, so that's penalizes false negatives. So it will a model with a high recall will never miss or will miss the malignant ones with lower probability. And so these two, precision and recall, are sort of the two sort of sides of accuracy. So we could do the same for just like with accuracy, we use the function from scikit-learn. Similarly, for precision and recall, we could use the function from scikit-learn. And so let's look at some of these numbers. Okay, so here we are seeing that, let me print the precision. So on some classes, the precision is 1, but on other classes, the precision is low. Similarly, recall. And same as with recall, but you also want to sort of balance the precision and recall. So you want a geometric average of these two. So F1 score is basically such a quantity, which is a single number that basically summarizes the performance of the model on a given class. So this is per class F1 scores. Okay, so that's that. Let me move to the next thing. Okay, so that was about accuracy metrics. Now let's move on to feature engineering. And let me see how much I have left. Okay, not much. So I'll quickly finish and then I'll take the questions. Feature engineering. So yeah, a data set consists of examples of form like X and Y, right? And as mentioned earlier, the inputs or the X's are called feature vectors. And then what is feature engineering? It's the process of converting raw data into useful feature vectors. So you might have images, and that's like the image. The raw image pixels are basically the raw data, but you want to sort of have transform them into a representation that's highly predictive of the target variable. So in the diabetes example, our feature vector consisted of like these age, gender, BMI, and so on. So you want to keep like so this came out of some feature engineering activity. And why do I say that? So for example, like look at the BMI, which is informative for predicting a disease or not, versus just height or weight. So if you give me the height of a person or just weight of a person, people come in all sorts of heights and weights. So it's not like someone might be really, really lean and they might have really large weight, or yeah, so that doesn't reflect like health, but BMI is slightly more useful and informative. So picking the right sort of features out of raw data is feature engineering. There are different types of features. The learning algorithms basically work with numerical feature vectors, but how about like features such as colors or weeks of the day? So if you have, let's say, color, and then you have some other like blood-related numerical features, then how do you represent this string as a numerical value? Then you can represent them using one-hot encoding. So you can have like, if you know that there are only 3 colors that you are going to deal with, red, green, and blue, then you can have a one-hot encoded vector like this. So red represents this vector represents a red color, this vector represents a green or a blue. You might ask, why not just put like red equal to 1, green equal to 2, and blue equal to 3? And the reason for that is because there is no relation. If we do that, 1, 2, 3, then that means we are somehow encoding this information of proximity, that red comes first and green is closer to red and blue is closer to green and further than red. So we don't want to sort of give the model this impression that there is some relationship between them. But if there are days of the week, then it makes sense to put in like 1, 2, 3, 4, 5, because Monday is closer to Tuesday, and it's further than Wednesday. So it makes sense to have Monday equal to 1 and Wednesday equal to 3. Okay. Sometimes for the optimization purposes, we need to normalize the data. So imagine you have a data set in which the features are of very sort of different magnitude. So you might have some feature which measures some quantity in the range of like thousands, and then there may be other feature that measures in like tens or even fractions of a unit. And so to deal with such sort of problems, like in such sort of unbalanced or wide range of feature values, the optimization doesn't work very well. And so we need to compress the range of the feature vectors to 0, between 0 or 1, or -1 and 1. And to do that, we can use normalization. So we find the minimum of the whole data set for that feature, and then we subtract the minimum. And this guarantees us that the minimum will always be 0 after this normalization. And then we divide it by the maximum of that feature minus the minimum of that feature. And this guarantees that the maximum of this value, the normalized value, will be equal to 1. So this basically helps in speeding up the learning and normalizing, speeding up the learning and avoiding numerical overflows. So in the next slide, I think I just sort of give a brief overview of like, if we not normalize even our sort of data set, the digits data set, which doesn't really need normalization, but even then we get some overflow errors or whatever, the convergence errors, and we get a 95% accuracy. But imagine we standardize it, so, or normalize it using this pre-processing primitive in scikit-learn. So if we do that, then the training goes without any errors and it converges, hopefully, yeah. And then we can calculate the accuracy. There is something going on in there. So probably we trained the model with X scaled, but we are evaluating it without the scaling. So now we have a lower accuracy. So we need to do the same for, so rather than providing the raw value, we need to provide the standardized values. And so if we do this, we get the same accuracy as before, but without the errors and so on. So anyway, another common problem in feature engineering is missing features. So you could have something like age, body mass index, average blood pressure, and so on, but sometimes some values would be missing. And so a part of the feature engineering is to basically either remove these examples where the features are missing, or replace it with an average value of the feature in the data set, or use another model to predict this value and then use that in the model. So that's it's called data imputation, and it's pretty sort of common in machine learning. Is this my last slide? Yes, so this is my last slide about underfitting and overfitting. So underfitting, it's a very sort of important concept in machine learning, and it goes back to the idea of like which model will you use. So the underfitting problem is the inability of the model to predict well the labels of the data it was trained on. So if you are not getting like good training loss, if you have really high training loss, then you might be underfitting. And the reason might be that your model is too simple. So your problem requires a neural network, but you are using linear regression. So that could be like one of the problems. The features you engineered are not informative enough. So, and the second problem, or the second sort of cause of underfitting, would be that maybe you are doing something like the inputs to the model are not informative. For example, you are predicting the direction of the car based on the pressure in the tire or whatever, like something, or like just predicting the wealth of a person from their face. Like if the features are not informative, then you can't do the prediction. So it's underfitting. Overfitting is the opposite of it. So the model predicts very well the training data, but performs poorly on the validation and test set. And so the way you identify this is if you have really low loss on the training set, but very high loss on the validation set. And this could be sort of fixed by reducing the complexity of a model. So maybe your problem requires a linear regression, but you are using a neural network. And the other one could be like, oh, you are using too many features. So to predict high blood pressure, you just need to sort of input a couple of features, but you have like input like the whole history of the person and so on. So it's just like too much information. It's overfitted to that particular person or particular data set. So that's the underfitting and overfitting problem. I would just move to the useful resource. So in the previous slide, I provided a link to a tutorial where you could do unsupervised learning by yourself. In terms of useful resources, when I was starting with machine learning, I took this course by NG a long time ago. I think it's still really useful. A lot of people really like it, so I've provided the link. And here is a sort of a recent book, the 100-page machine learning book, which is really quick to read. So I would recommend if you are starting out your journey, I think it's good to sort of read through a book. Yeah, so that's my presentation. I will take any questions.
Thank you so much, Dr. Khan. It was very interesting. We covered like a lot of interesting things in machine learning and useful things. And actually, it raised a lot of questions in the chat. The chat has been really active during the presentation. So I think it raised a good interest. So that's great. We do have some questions in the chat. And now please feel free to post on the chat or even unmute if no one is speaking to ask your question. I'm going to ask the first one from Marilyn. So do you just keep training until you're happy with the accuracy, or would you abandon your model and try a different one if it wasn't accurate enough?
Yes. It's a good question. Usually when you are trying to train a model, you want to so first you do in the beginning you do your due diligence as to like what the problem is, what sort of common task that you want to apply. Then you, let's say it's a classification problem, then you select like, okay, can the simplest model work? So let's say you start with logistic regression, and you set up like a lot of plotting. So let's say this is like the training iterations, right? Iterations, like, or let me just call it time. So as time goes by, and this is your loss function, and on the training set. So this is your J. So when you are training, you just like plot this over time and see if it is like converging to a value. So if it is not converging, then you need to tweak some parameters. So any model has a bunch of parameters, right? Like if it is, let's say, logistic regression, and you are using gradient descent, then you should sort of change the learning rate maybe a little bit, and then see. And if it turns out that okay, that's still not working, then you move to a little more complex model. So you might want to try some like a neural network or a decision tree, and then see how your loss function sort of on the training set works out. And if on the training set you achieve like a better convergence or performance, then you look into the validation set area, where like, is your validation set, so the green one is the validation set loss function, and you see whether it's coming down or not. And it will come down up to a point, and then it will sort of start increasing, and this is the point where you stop the training. So it's more sort of like there is quite a bit of art involved in when to sort of persevere and when to just pivot to the next model. So that's but the question is good, really good. Like, okay, when do we sort of throw it away? So there is not a simple answer, but like doing a bunch of analysis and sort of really looking at different metrics over time. I think that's the way to go.
Thank you. And that also explains why we need like the train, validation, and test set. So yeah, thank you very much. We have two questions, but I think they are mostly for the team. The first one is, will there be assignments given to help solidify our understanding? I think you can already play around with the code because you will have access to all the notebooks. And also during the phase 2, you will have plenty of time to apply the algorithms you have learned. And there's another question about the slides and the recordings. So the notebooks will be made available through a drive. We will send the link as a reminder for next workshop. And also the YouTube channel will be set. For now, we are having trouble uploading them, but it's going to be fixed in the coming days. So you will have the YouTube channel and the drive with the collab notebooks available, and we will send the links on the email. So now we have a question from Farzan for Dr. Khan. Is it possible to simulate the 3D liquid that flows on the plot as an optimizer, where the most of the weight of the liquid finds a stable position? We can assume that it is a global minimum. It contains some detail, but my question is that it is possible and worth to research for improving the accuracy to find the global minimum. Okay, so would having this 3D liquid thing help finding the global minimum? I think that's the question.
Yes. So the question is sort of a good one, whether we can incorporate some sort of physics into the model in order to improve the model performance, right? So one thing that you could look into is something called physics-informed neural networks. I don't know why when we think of machine learning, we always go to neural networks, but like that's the active area. So physics-informed neural networks is one area which you could look into. And what it basically does is we have this objective function as a function of the data and as a function of the model parameter theta or W. But along with that, if you have the simulation of the 3D fluid or the blood or whatnot, there would be like the differential equations of that simulation or that fluid dynamics basically provides additional constraints on this model. So there is a second component to it, which is basically the physics constraint, the physical constraint on the data. And so when the network is trained with this physical constraint, then it has better performance, and there might be like really good but you could look into the physics informed neural networks literature. There is some really cool stuff there. There was something that I wanted to show here where yeah, okay, I can't find the image, but it's a really typical image where you have a normal neural network. If you train it on data from here to here in this region, and then you, let's say it's a sine wave trained here, and then it will just go like this, like on this area. But if you train the physics informed neural network, then it will generalize even in the area where like it's not trained on. So it somehow helps with the optimization problem, because given this data and the physics constraints, you know that you would be in this region. So anyway, yeah, just my few thoughts on incorporating the blend dynamics.
I also want to add that when you go at very high dimensional data, the chance to get stuck in local minima is decreasing more and more. And the reason is that when you have, let's say, a few thousand or a million dimension actually that you are optimizing, the chance that across all of those dimension, the movement or changing gradients actually across all of them lead to improving the cost function is very, very low. So for small, low dimensional data, yes, local optimize is a big deal, but for really large dimensional data, that actually is the area when we have these machine learning neural networks, actually, it's not a big challenge. You don't see it that common.
Thank you very much to you both. I see a lot of thank you in the chat. Thank you for the great lecture, but no questions for now. So maybe I can ask one. We talked a lot about gradient descent. Do all the machine learning algorithms need this gradient descent process?
That's a good question. Yeah. So somehow, as we mentioned, like we need to do this this optimization of the cost function with respect to weights and the data, like given the data, and we need to find this W star. So in some cases, this optimization could be sort of done in a closed form. So let's say if we have linear regression, we can provide a closed form solution called the normal equations. So in that case, we don't need to sort of use gradient descent. There are other sort of black box optimization sort of methods that are sort of used for some machine learning problems. But most of the time, since our models are sort of differentiable, gradient descent is the most common or popular method to use for machine learning training.
Thank you very much.
You might have more to say on
Marilyn asked a follow question. I think it's good to explain the reshape function a little bit. So she asked, maybe this was already explained, but the dimension of data is the dimension of the data the amount of elements in the input vector. So previously, Sebastian and Farhad both explained a little bit more about that. Maybe we can just talk a little bit about the dimensionality of our data and then reshaping.
Yeah. Yes. So I could explain the point made by Dr. Maliki. So if you have, let's say, one dimension, and we are talking about the input dimension or the number of the parameters of model. So if it is a linear model, linear regression, then the input dimension basically determines the number of weights in the model, right? Like if there are 3 inputs, then there are like 3 weights. But if it is a neural network, you could arbitrarily increase. So there are 3 inputs, but internally you could have like so many sort of neurons, and so now you have like 3 for 1 neuron, but then 1, 2, 3, 4, 5. So you have 15 in here, 15 weights in here, and then you have 5 times 3, so 15 weights in here. So you have 30-dimensional sort of landscape of the cost function. And so let's say you have the just only 1-dimensional weights, so W1, let's say, and this is your J, the cost function. So if you have some sort of like this sort of loss function, right? So in this case, you can get stuck in this local minima, because like left there is like like it's higher on the left and higher on the right. So there is more chance that you will get stuck in here. But if you have multiple dimensions, so if let me take it to this 2 dimensions. So even though like there is like in this dimension, it's like it's you can't go in left or right, but you could go like maybe on the second dimension, second snapshot of it is like completely flat, or maybe even like here. So the second dimension, like you can't escape the first dimension, but like you can go left or right, but you could maybe go out or inward into this surface. So even though like in the single dimension you are stuck in this local minima, since there are more dimensions you could walk across, you could sort of go left, or go outward or inward in this second 2D dimension. I'm not good at drawing, so I can't illustrate this point, but you get the idea that in one dimension you don't have anywhere to go, but in multiple dimensions, maybe one of the multiple dimensions might allow you to basically decrease in the class. Hopefully that gives some perspective on that.
Yeah, thank you. I'll regarding the question on reshape, I should say that sometimes perhaps for those of you who have been able to work with libraries like NumPy, and you'll learn more in regarding NumPy and Tensor, actually libraries like PyTorch. Vector-based computation is way easier compared to, or way faster, more efficient. And this is the reason both in PyTorch, TensorFlow, or even when we use CPU, we use NumPy to increase the speed of computation. So we work with vectors. And when we design these models, neural network models, we need to make sure that the input vector and output vectors, when, for example, you can't add let's say, two vectors of different size together. So that's where reshaping comes to the middle. So you might have sometimes you need to flatten a 2D image to make a vector out of it, or sometimes you need to go back, actually make a 2D version to visualize it. That's something. Regarding the previous questions on the regarding difference, is the let's say this updating gradient is the only approach for finding the best model or best, let's say, in AI or artificial intelligence? And the answer, as Dr. Khan suggested, no. But this one is the most common one that we use, more specifically in neural networks. There are other approaches to find, and some of them actually are just search-based. You can search among different, let's say, models that help you. But in general, when it goes to a large model, those approaches are not practical. And the state of the art actually is based on updating gradient, and they are gradient-based.
Thank you very much. We have a last question on the chat from Henry. How can one be sure if the data obtained from the model is sufficient enough to prove its own premises? Is there a certain standard to determine the efficiency of the information from our models?
Yeah, so the reason we divide the data set into these different buckets is to basically have some confidence on where is the, yeah, here. So the way we figure out whether the model, the output of the model is confident or like is reasonable to be trusted or not is using this validation and test set. So we train the model on some training set, and then on some test set we evaluate whether we predict, or the model predict correctly or not. And if the model predicts only 80% of the time correctly, then we say the model's accuracy is 80%, and so you should just only rely on it if 80% of accuracy is good enough for you. So basically, evaluating on an unseen test set is the way to sort of evaluate whether the model is performing good or not. I'm not sure if that was the intention of the question or if I misunderstood it.
I think you understand it well. We need the validation data set to check if what we've learned is sufficient. I think we are out of time right now, so maybe we should close the session. Thank you very much, Dr. Khan, for this very interesting talk. Everyone, you will have next weekend presentations about specific machine learning algorithm applied to problems. So we'll go deeper into that. And yeah, we look forward to seeing you all next week. And thank you very much, Dr. Khan, for today's presentation.
Thank you. And thank you everyone for your very active participation today. It's definitely going to work in your benefit and help us with the phase 2 research as well. So see you next time on Wednesday. Bye.
Thank you.